To understand the scale of energy locked inside an atom, we have to start with its basic building blocks, protons and neutrons. Logic dictates that if you weigh a handful of these particles individually and then bind them together into a single nucleus and weigh it again, the total mass should be exactly the same. But when we actually measure this, the math breaks down. A fully assembled nucleus is measurably lighter than the sum of its isolated free-floating parts. Looking at the physics manuscript, we see this missing mass formally defined as the mass defect. We can express this discrepancy algebraically to calculate exactly how much mass vanishes when a specific nucleus forms. First, we take the number of protons, represented by the variable z, and multiply it by the resting mass of a single proton. Next, we add the mass of the neutrons. We find this by taking the atomic mass number, A, subtracting the protons, and multiplying that result by the mass of a single neutron. That gives us the theoretical total mass. Finally, we subtract the actual measured mass of the assembled nucleus, represented by capital M. The result is a positive number. This missing mass is not a rounding error or a glitch in our equipment. It is the core physical currency of atomic stability and the ultimate fuel source driving the universe. So where exactly does this missing mass go when an atom binds together? This document contains the answer: mass-energy equivalence. The lost mass converts directly into pure energy, creating binding energy. It's the exact energy needed to split a nucleus, or released when formed. To calculate efficiently, multiply the mass defect by 931.5 to get mega-electron volts. Let's put this theory into practice by calculating the binding energy of a standard helium nucleus. We start with the resting mass constants at the top: proton, neutron, and helium. Plugging these into our equation, we subtract the assembled weight from the isolated particles. This reveals a net mass defect of 0.0305 units. Finally, we multiply this by 931.5. The result is 28.4 mega-electron volts. That absolute value is the total energy physically locking a single atom of helium together. It is tempting to look at a high total binding energy and assume the atom is highly stable, but looking solely at the total energy pool is misleading. A massive nucleus like uranium has an enormous total binding energy simply because it contains so many particles, yet uranium is highly unstable and prone to decay. To accurately compare atomic stability, physicists rely on a normalized metric, binding energy per nucleon. We take the total binding energy and divide it by the mass number A, the total count of protons and neutrons. If we return to our helium calculation, we take that total 28.4 mega-electron volts and divide it equally among its 4 constituent nucleons. This gives us 7.1 mega-electron volts per nucleon. As the text states, the greater this per nucleon value, the greater the overall stability of the nucleus. Nature inherently favors atomic configurations that maximize this average energy. This constant structural preference is the invisible engine powering all nuclear reactions. We can now shift our framework from the static stability of single atoms to dynamic nuclear reactions, specifically nuclear fusion. The bottom equation on this page dictates the universal rule for these reactions. The total energy released is simply the sum of the binding energies of the resulting products, minus the sum of the binding energies of the initial reactants. We can test this rule against the extreme conditions inside a star, analyzing the triple alpha process responsible for synthesizing carbon. In this high-temperature environment, 3 distinct helium nuclei collide with enough force to merge into a single carbon nucleus. Looking at this reaction equation, we calculate the mass difference between the helium reactants and carbon product. The 3 helium atoms are slightly heavier, leaving a mass defect of 0.0006 atomic mass units. We multiply this by 931.5, yielding 0.56 mega-electron volts of pure energy. We can prove this works universally by looking at this hypothetical equation, fusing 2 different isotopes of hydrogen into helium. Instead of using specific resting masses, we assign arbitrary variables, A, B, and C, to represent the binding energy per nucleon for each isotope in the sequence. To find the total energy of our product, we multiply the per nucleon energy, C, by helium's 4 nucleons. For our reactants, we multiply the first hydrogen isotope's energy by its single nucleon and the second by its 3 nucleons. Subtracting the reactant's total energy from the products yields the final formula, 4C minus A minus 3B. The immense power of stellar fusion is entirely predictable through this strict arithmetic of missing mass, the universe's ultimate energy ledger.